Watch the coffee. One jolt and the quick ripples are gone in a breath. But there's always one slow wave that keeps rocking, long after the surface should be still. Same jolt, same cup. Why does one ripple vanish at once and another keep moving? The answer is in the shape it settles toward. A fit sits where the surface is level, the best the model can do. Nudge a parameter, and the fit gets worse. It pulls back toward level. How hard it pulls back is the curvature, the Hessian. The Hessian is just how fast the fit worsens as you move off the best value. In non-mem, it's the curvature of the objective function. In machine learning, the curvature of the loss, the same matrix. But not every cup sloshes the same. A tall, narrow cup is stiff, the surface snaps back. Vast, a quick ripple. A wide, shallow bowl is soft, it sways. Slow, a long, lazy slosh. Different shapes, different rhythms. Every surface has pure sloshing patterns, its eigenvectors, and each one rocks at its own rate, set by its curvature, its eigenvalue. An eigenvector is a pure direction of the bowl. Its eigenvalue is how steep it is that way. Steep curvature, fast rhythm, the frequency goes as the square root of the curvature. Line the rhythms up, fastest to slowest, that's the spectrum. The whole story is just two of them, the fastest and the slowest. Their ratio is the condition number, the largest curvature, divided by the smallest. Widen the slow vessel, soften that direction, and the condition number climbs without limit, while the shape stretches from a round cup to a long, shallow tray. Non-mem prints this as the condition number. Past about 1,000, treat it as a warning. Now carry it. Each footstep is a little jolt. The tall cup barely notices, but the wide bowl's long, slow slosh climbs the side and goes over the rim. The jolting finds the floppy direction. Random noise in the data is that jolting. How far each direction sloshes is its uncertainty, and it's the inverse of the curvature. The covariance, H inverse, the standard error along a direction, goes as 1 divided by the root of its curvature, so the stiff direction is pinned, and the soft one is barely known. And what's barely known isn't a single parameter, it's a combination, the way the long slosh runs. What settles fast, you know. What lingers, you don't. The table's gone still. The surface is almost calm, except one slow wave, still rocking from side to side. The slowest rhythm is the last to settle. And that sets how long everything takes. An optimizer working this shape is gated by the slowest mode. Plain gradient descent shrinks the error by the condition number -1, divided by the condition number +1. Each step so a long tray crawls, sloshing back and forth across the narrow way while it inches down the long one. The cure is to stop walking and reshape. Newton's step multiplies by H inverse, it rerounds the tray into a cup and settles in one move. BFGS approximates that. Atom is a cheap version that rescales each direction on its own. Widen it further until the surface barely pulls back at all, a nearly flat tray. Now the tiniest disturbance round off. A noisy gradient sends the slow slosh drifting, magnified by the condition number. The step that computes the uncertainty is a division by that curvature. Near zero, it blows up. This is the rounding error failure, when the matrix turns singular. It's the same trap as weighing one almond by subtracting two big numbers, a real signal lost in the noise. The fix is to measure it directly. So can you always calm a slow slosh? Sometimes. If it's a wide bowl that still has walls, still pulls back, narrow it. Rescale the parameters, precondition the problem, and it settles faster. The trouble was practical, and it's gone. But sometimes the coffee sits in a level channel. Open along its length, it never pulls back. It just flows from end to end. No reshaping gives it a bottom. The data can never pin that direction, and the eigenvector of the smallest curvature names exactly which combination it is. That's structural. No optimizer, no rescaling fixes it, only a different experiment, or capping it with prior knowledge. It's the sugar and honey problem. When nothing you can measure tells two things apart, only a choice breaks the tie. One surface. Its curvature is the Hessian. Its pure rhythms are the eigendirections. Their ratio, the condition number. The inverse of the curvature is what you know. The slowest slosh is what you don't, and whether you can fix it depends on whether it pulls back at all. Back to the cup. Now you can see it. The slosh that keeps rocking is the direction you least know. What settles fast, you know. What lingers, you don't. The quick ripples settled in a breath. The long slash how long? Exactly, that's the next question.